Hi, I'm Fabio, and welcome to the fourth course of our Machine Learning Mathematical Foundation course series. In this course, we will talk about calculus. In particular, calculus studies the continuous changes. And there are two major branches about calculus, the differential calculus and the integral calculus. These two subjects are related to each other by the fundamental theorem of calculus. So, in the next slides, we will develop tools that will allow us to study and measure how things change and accumulate, for example, over time. Let's wrap up what we've covered in the previous courses. For example, in the course number 1, we've talked about vector spaces, which is the obvious, we could say, a space where we can introduce operation and properties between its elements. We have defined matrices, a particular type of elements in vector spaces, and the bases, which are our point of view about a vector space. In the second course about analytic geometry, we've studied inner products, which induces norms to define the length of vectors, and metrics to measure the distance between two vectors. Then, thanks to the concept of inner product, we have defined what orthogonal projections are, and finally what rotations are, and in particular we described the rotation linear mapping in 2 dimensions with its rotation metrics. In the third course we've deep dive into the concept of linear algebra and analytic geometry, introducing the determinant, which is a particular function in a vector space that measures the way a linear mapping changes the volume and how the vectors are stretched and rotated through this linear mapping. Then we have defined some, we can say, constants of a linear mapping that can describe in an easier way the linear mapping, which are eigenvectors and eigenvalues. And we've found how we can compute them using the determinant. Then, in the last part of the third course, we have talked about how to simplify a matrix. And remember that a linear mapping can be described by a transformation matrix. So, in order to simplify, to write the linear mapping in an easy way, we can simplify its metrics, its associated metrics. We can do this by eigen decomposition, if we can do this, because the matrix is squared, and we can transform it to a diagonal matrix. If the eigen decomposition is not possible to be applied, then we can use another type of decomposition, for example the Cholesky decomposition, or in more general cases the singular vector decomposition. So let's move on and talk about calculus. In this course we will talk about topology, differentiation, how to use the differentiation, and thanks to approximations and automatic differentiations. And finally we will introduce integration, that we will cover also in the next course, talking about statistics and probability. So let's move on to the first section of this course, topology. And we will see that this mathematical subject is the mathematical version of our workbench. So it's the space where we can work with function in an easy way. generic easing function. And remember that our goal here is to measure how things change. So in order to do so, we need a space where these variations, these changes, can be easily computed. And we can do this introducing the topology. In particular, in this section, we will see first the most generic approach to introduce, and also more abstract approach to introduce the topology subject, and then we will make it more concrete. And this specific subject will be used in the next sections. So, talking about a topology, what is a topology? Let's say we are approaching this subject using the more generical approach. So let's take a generic set of elements. Could be fruits, apple, oranges, and so on, or could be numbers. Doesn't matter. We take this space omega, and we define a topology tau, which is a collection of subsets of omega, such that the elements of the tau, those subsets, respect three properties. The first one is that the empty space or the wall space are lie inside the topology. Okay, because remember, tau is a collection of subsets. So these two elements must lie inside tau. Then we have the other two properties. In the first one, let's say that E is a subset of indices, and we take a discrete number of subsets ui, and we say that each of these lies into tau, into our topology. Then, if tau is a topology, then the discrete union of these subsets must lie on the topology too. Third property, we take two of these subsets that lie into tau, and if tau is a topology, then the intersection between these two sets must lie in the topology too. So the second property is here can be expressed as that the topology is closed under finite union. Finite because we take I, capital AI here, as a set of finite indices. The third property could be expressed as that the topology is closed under arbitrary intersection of closed sets. We say that it's closed because if we take the elements and we apply the property, here we have that it's closed under finite union. In fact, here we apply the union. Here we say that closed under intersection. Closed because taking the elements, even applying this property, then the result also stays in the topology. Okay, so given a set of elements, omega, we can try to find a topology. So the couple omega and tau defines what is called the topological space, and the elements of a topology are said to be open sets. We will see that we can find, given a generic set of elements, we can find multiple types of topologies. And here I want to show you a particular one, the power set, which is also indicated by P of omega. and the power set is the collection of all possible subsets of omega. Of course, as I mentioned 1 minute ago, the power set is a topology on omega. Let's see an example to better understand what the power set is. And let's take this omega, a set of two elements. Could be two numbers, A and B, for example 1 and 2, could be apples and bananas. That's the same. Then the power set is all the collection of all possible subsets of omega. So which are the all possible subsets there? We take nothing. We take the first element, the second element, and we take both, which is equal to omega. As you can see, the power set here respects the three properties that define what a topology is. For example, you can see that the first topology is easily proved because the empty set and the omega lie onto the power set. But as I was mentioning before, the topology is not unique. In fact, for example, we can, given this omega, define the trivial topology, which contains only as elements only the empty set and the whole set. Now we have defined the space where we are going to play a little bit in. So let's take an element of omega. For example, could be a banana from before, and we define a neighbor of this element, a neighbor of x, as a subset I of x that stays, that is a subset of omega, such that we are able, if this u, which is a subset that still lies in tau, if we are able to find a u, then the subset is a neighbor of x if x is in u, which stays in y of x, which of course, as before, stays inside omega. Here I is a function. In fact, assigns to each point we will refer of the elements of omega as points in the next slides. So assigns to each element, to each point in omega, a non-empty subset, of course Ix, that stays in omega. So here what we are saying about a neighbor of x, this is a neighbor of x, if we are able to find some set that stays inside I of x and is on the topology, refers to the subset in a topology, and also x stays in U. So let's see this thanks to this example. And here we will not talk about x but p, the point p. And let's assume that omega is the 2D plane. Looking at the picture here, that's the point P. And we can say that V is a neighbor of P because we can find a U in the topology. We will see next that we can define a topology on R2 to the power of 2. That's not a problem. We can find U here, this circle, in which P stays inside a circle, inside U, and also U lies inside V. So a set V in the plane is a neighborhood of the point P, because we can find a small disk U here around P that contains P, and also the small disk U is contained in V. Now, thanks to the concept of a neighborhood of a point, we will define what an interior point of a subset of omega is. So let's consider the generic element x inside omega, and a subset of omega, which will be called S. So x is an interior point of S if we are able to find a neighborhood of x such that x lies into its neighborhood, okay, but also the neighborhood is a subset of S. So x is an interior point of S if we can find a neighborhood of x that lies inside S. Okay. So if we take a point and we find a neighborhood around him that lies inside S, then x is an interior point of S. Okay. Is interior. And also we will say that the set of all interior points, so the collection of every x that is interior point of S, will be the interior of S, and will be also denoted by this notation. So here we say that x is an interior point of S. If we take all the interior points of S and we collect them together, that's the interior of S. We can do the same, but defining what an adherent point is. And we say that x is an adherent point of S if we take all possible neighborhoods of x, we will always find an intersection between the neighborhood and S that is a non-empty. Before to define the interior point, we were searching for one neighborhood that lies inside, that is contained under S. In the other point, we search for every neighborhood, and we say that if there's a non-null intersection between whatever neighborhood we choose and S, then x is an adherent point of S. If we collect together all the adherent points of S, we find the closure of S. That is denoted thanks to this symbol, to this notation, the bar above the set. Here we say that x is an adherent point of S if x always belongs to its neighborhood I of x. So if x is inside S, then of course we can always find a neighborhood that has a non-null intersection with S. So if x stays inside S, that's no problem. This will be for sure an adherent point. But here, thanks to this definition, x doesn't need to lie inside S. Could be external of our set, but still be an adherent point of that S. Finally, we define the third concept here, which is the boundary point of S. So x lies on the boundary of S, simply if it lies on S but not in the closure of S, but not in the interior of S. So the boundary, which is in fact this denoted by this notation, the boundary of a subset S of a topological space, the omega, is the set of all points that can be approached both from S and from the outside of S. The boundary, in fact, as the name says. So let's take a look to this example and express in a little bit more concrete way what interior points, other endpoints, and the boundary are. Let's start taking a look to X. Previously, that's what we've called as P. So we can always find a neighborhood for X, this disk, such that X stays inside the neighborhood and the neighborhood is inside S. That's our space S. Okay, so X is an interior point of S. Good. Now let's take a look to Y. Y is in the border of S, we could say. In fact, we will see in a moment that the point Y is on the boundary of S. So here, let's first define to find what to prove what Y actually is. Let's find the interior of S, and we already found one point here that is an interior point of S, which is our X. If we move X, when we can always find a neighborhood of X such that this expression is always proved? Well, when we move the point around S but not in the border, because in the boundary here, the border of S, for example in here, we can see that yes, we can find a neighborhood of here is Y. Y lies inside the disk, but it doesn't stay fully inside S. This expression for Y is not satisfied. Now take a look to the closure. So the Y is another endpoint if we for every neighborhood of Y, we can always say that the intersection between its neighborhood and S is not empty. Well, that's pretty straightforward. And again, since Y is not an interior point, then if we search for whatever neighborhood of Y, we always find that Y stays inside its neighborhood, but is not a subset of S. So in here we find in the first expression, we find that Y is another endpoint, but in the second one we express that Y is not an interior point of S. When we get that Y stays here but not here, then it means that Y is on the boundary of S, in the border. Thanks to the definition of closure in particular, we can define another property for an element in a topological space. In fact, given, let's consider now an x of 0 element that stays inside omega, and let's consider S as a subset of omega. In here, as noted on the bottom right corner, x0 doesn't need to be inside S. Okay. And we say that here is x0 is an accumulation point of S if we consider whatever for all neighborhood of x0, we are always able to find another element x that lies inside S, and x is inside the neighborhood of x0, and x is not x0. So when x0 is an accumulation point of S, we can zoom how much we want around x0. So this means we can always we can define whatever neighborhood we want, smaller or bigger as we prefer. But we can zoom how much we want around the x0, but we will always find at least one point different from x0 that stays inside S. Here we express this concept in a graphical way. So this is our point of accumulation, and we can zoom how much we want. Here we have a bigger neighborhood for this point, for the black dot. And we can find, for example, 3 red dots that lie inside our set. So with this neighborhood, we can always find an x that lies inside this, and we can zoom. We can choose smaller disks, which are smaller neighborhoods, and we always find at least one red dot that lies inside the green space. So this is a point of accumulation. And we can see this better using, finally, we can say, numbers. And in particular, here we consider the real line. Or better, the closed set between 0 and 1. And we define our space, our subset of omega, as the set of every element defined in this way. So, for example, when n is equal to 0, then the element x of n is equal to 0 over 1. Okay, that's it. And so on. For example, here, if let's take this one, if n is equal to 4, then it's 4 over 5, this element, and so on. We can see that the element plus 1, the element 1, does not lie inside S. In fact, how we can get this equal to 1? We can reverse the equation pointing saying that xn is equal to 1, and we find that n plus 1 is equal to n. This is impossible. So S does not contain 1, for sure. But we can say that it's an accumulation point for S, because we can try to zoom in how much we want near plus 1, but we will always find an element of S that lies into our neighborhood of plus 1. So plus 1 is not in S, but is an accumulation point for S. And this is important. And in fact, the accumulation points are also known as limit points, because they allow us to introduce a new concept, very important, fundamental in the calculus subject, which is the concept of limit. So let's take two topological spaces, one defined over omega and one defined over theta. And here we define also a function that goes from omega to theta. And we say that x0 is an accumulation point and stays inside omega. So here we will have x0, and on theta we will have f of x0. We define L as the limit of f of x as x approaches x0, which will be, since we don't want to say this every time, we will write this down. So L in the uppercase L will be the limit of f of x as x approaches x0. The value L will be the value such that this expression is satisfied. And here we have to slow down a little bit and look at every element. So with I of L, we say that are the neighborhood families with respect to L. And here I of x0 with these graphs will be the neighborhood family with respect to x0. So for here we say that for each neighborhood of L that we choose exists one neighborhood U for x0 such that f of U, in which we don't consider x0, the image of U through f will be a subset of V. So basically, the points that are inside the neighborhood of x0 are mapped inside V thanks to f. Again, here we have a neighborhood of L. Here we have a neighborhood of x0. Then we say that the neighborhood of x0, without considering x0 itself. So the neighborhood of x0 will be mapped, thanks to f, to the neighborhood of L. And L will be the limit value. So we have the limit. When we want to find the limit, we are just searching for which point satisfied, which L point satisfies this relationship. Here is written better, I would say. So L is the value for which I'm always, here it's always, able to find a neighborhood of x0. Here is to find a neighbor exists, to find a neighborhood of x0, such that through f, its image, the image of the neighborhood of x0, is in the neighborhood of L. Let's see this in a graphical way. Here we have our point x0. Here is expressed as x. And we have this will be our omega, and this will be the image of f. In here we say that this point L will be a limit if we map u, except for x0 that in this picture is written as x. If we map this through f, then the image of fu will lie inside V, and V is a neighborhood for our limit. And remember, we can choose the neighbor we want. So V could be how smaller we want, closer to the limit, but we will always be able to find another neighbor, maybe smaller, very small or very big, doesn't matter, that f and the image of this neighbor will map inside our smaller V. Thanks to the concept of limit, we can define, we can characterize the function as continuous if respects a particular property, and this is one. So f is continuous at a point x if we chosen whatever neighborhood of x we want, we will always be able to find u in the topology such that x will lie inside u, and u will be a subset of the counter image of V. So the counter image of V is a neighborhood of x. For whatever neighborhood of V we choose, such that V is a neighborhood of f of x in theta, the codomain. And this can be seen in this picture. So here we take our domain, the input space is called here, and we say that the image is continuous if taking whatever, here for example x lies inside, f of x lies inside here, the output subset, then we will always be able to find a u such that x is inside u and will be in the counter image of V. Let's see this in a more detail. Input space, the function is continuous at a point if, let's take a point, output space, the codomain. So no matter how much we zoom in around the output point, remember that we are in the accumulation point. So no matter how much we choose this neighborhood for the blue dot, we can zoom in around the input, the x. This is the blue dot is f of x, and the green dot is x. So no matter how much we zoom in around the output point, the f of x, this circle represents the neighborhood. Then we can zoom in around x, our input point, such that we map, if we do f of x selecting one of the points inside the green disk, we will always go inside the blue disk. That's the continuity. If we move a little bit around the green dot, we will always move a little bit around f of that point. So smaller changes in the input space are reflected through this function with the smaller changes in the output space. That's why we say that the function is continuous. In particular, if f is continuous under every point in the domain, in its domain, omega, then f is said to be, in a more generic way, continuous. In particular, we will say that we can see the continuous functions as functions that can be written, for example, onto a paper without leaving the pen from the paper. So if we keep writing the function, the graph of the function, then the function will be continuous here. That's an approximated way, an empirical way to describe if f is continuous or not. We've defined the main concepts about the topological spaces, but I want to show you something curious only using this slide, that using the topological spaces we can define particular continuous functions between topological spaces, the homomorphisms. And the homomorphism formalizes the intuitive idea of deformation without tearing. For example, this mug can be deformed into a torus without tearing the object. That's something curious, interesting. But now we have completed the more abstract topic about the topological spaces, and we can move from generic and abstract notation to something more concrete. That's the case of the real space. So wrapping up what we have seen since now is that depends on two concepts. The open sets, we've talked about topology and the elements of a topology, so which are the open sets. And also we have defined the interior of a subset of omega, the other endpoints, and so on, using the concept of neighborhood of a point. Now we have to describe the open set and the neighborhood of a point in a more concrete way inside the real space. So let's start with open set. And in order to find what open sets are in real spaces, we define an open interval. Here we are on the real line, and we define the open interval such that it's pretty straightforward. Here A could be a generic real value or minus infinity, and the same for B. So we could find that open intervals are open sets, and define a topology on the collection of those open intervals are a topology on our real line. From course 2, we've seen that we are able to define a metric on R, such that R and this metric is a metric space. Thanks to the metric space, we can compute distances between elements in the real space. Again, here, given omega, a generic set of elements, the metric always induces a topology on omega. That's we will not prove this concept, but we can. How can we use metric and with this the metric space to induce a topology on omega? Well, we just have to define a ball, what is called a ball, with center x0 and a radius r. What is a ball? Well, is a collection of all elements that are far from x0 at maximum r, or better, almost r, because that's not unequal here. So this is an open ball. The collection of all kind of balls, open balls, we can define on the R space, can be described when taking the balls with respect every element on x0 inside omega and a positive radius. So the collection of all these balls, B, is a topology on omega. That's the most general concept. So to do this on the real space, well, we just have to describe D. How we can describe D? But first I want to dig down onto the concept of open ball and use it to describe also the neighborhood of a point, which is the second element we've talked so far, to introduce the interior point, the adherent point, the boundary, and so on. So the open ball centered in x0 is a neighborhood of x0. Why? Because that's the definition of a neighborhood, in which it means that we can always find a delta, a number delta, a real number that is less than the radius, and U will be here will be a subset for the ball, which our name is our neighborhood. This means that B of x0 r is a neighborhood of x0, because we can always find an open ball centered in x0 but smaller than what we have defined so far. That's it. This proves this definition, which is the definition of a neighborhood. In the real space, we usually consider to define the ball the Euclidean distance. That's it. So the Euclidean distance, the Euclidean distance in a 3-dimension is a sphere, and the 2D ball is a disk and in the 1D ball is a segment. So in real spaces, we can use open balls as neighborhoods and open intervals as open sets. That's what we have found so far. And thanks to this, we can decline the concept of a limit inside the real space. Here is the definition that we've seen previously about the limit. This is the relationship that goes through L and x0 to L be the limit. Now let's rewrite this, considering that the neighborhood will be an open ball. So here we saying that for all neighborhoods of L, it means that whatever radius epsilon we choose, the ball be centered in L and radius epsilon will be ... Then we consider here for excuse me, that's a mistake here, is exist U inside, so it means that exist a neighborhood of x0. It means that we can find delta, a radius, for the ball, the open ball, centered in x0 and with radius delta. This concept here can be rewrite as what? So f of every element in this ball. So f of x for each of the elements inside the open ball centered in x0 and with radius delta. Of course, we do not consider x0 itself. And this set of f of x will lie inside the open ball centered in L and with radius epsilon. This expression can be simplified saying that for all epsilon, positive epsilon, exists a positive delta such that the distance between x and x0 is less than delta, then the distance between f of x and L is less than epsilon. That's exactly as before, in which we have to, for all epsilon, for exist a delta, this will let this true notation in standby. Then we say what? We have to consider that x here lies onto the ball. So this is written here, x inside this ball. So the distance between x and x0 is positive, so we don't consider when x is equal to x0, that's this term, but it's less than delta, which means that x stays inside this open ball. Then what? That's the right term here. Then f of x, distance between L, less than epsilon. So it means this means that stays inside the open ball centered in L and with radius epsilon. This is or better, these two, since we use the Euclidean distance as the distance itself, this is the usual expression of a limit inside the context of our real space. Now we can characterize even better what our limit is. Why? Because let's see that here we don't have x0 because the picture is taken from the Wikipedia here, but we have c. So L is the limit of c. What does it mean? It means that for all epsilon we choose, we can always find a delta such that every point x inside this range will have its image. That's, for example, let's take this point here. The image will measure from L, our limit, less than epsilon. In fact, here we have it. So that's x, we move, the image lies inside the open ball centered in L and with radius epsilon. But the limit, remember that the limit for a point is defined with respect to every accumulation point, not every element in the domain. Remember what we have seen so far, the example we have seen for the 0-1 segment with the series that converges to 1, but S did not contain the element 1. And 1 was still an accumulation point for S. That's the same for the limit. We can compute the limit of a function. For example, here we say that we can compute the limit using x equal to plus infinity. Because from x greater than this s, the distance will be less than epsilon with respect to L. So we can, for example, compute the limit for points that are not in the domain of a function. For example, plus infinity, since it doesn't even lie into the real space, but we have added up to the real space. So note that through this definition of limit of f of x, x can approach x of x0 from whatever direction, and to exist, the limit, the value of L, must be always the same. So in here, looking at the left image, we can approach C and then L from the right to the left, using points from the right to the left or from the left to the right. That's what we are expressing here. And that's why we can decompose the limit to its left-hand limit and the right-hand limit. For example, in the left-hand limit, we consider only the left part of the 1D open ball. And that's what the limit is. So we say that the function has an existing limit in that point if the left-hand limit is equal to the right-hand limit. But this is not always true. For example, this function in the middle is not continuous, and we've seen that the function is continuous if it has a limit in it. Because if we compute the right-hand limit, we find that this value is L. But if we compute the left-hand limit of this function, we find this value. And these two values are not the same. It means that here we cannot compute the limit. The limit does not exist. And then the function is not continuous. Even here with an hole, the function is not continuous, because to write it down, this function, we have to we cannot maintain the pen onto the paper to write it. But here this problem could be easily fixed, just taking the limit of this point, which is an accumulation point, because we have just a point with respect to one hole. Because we have one hole with respect to only one point. That's it. And here with vertical asymptote, the function is not continuous. So this is the. So far we have talked about the deep dive onto topology, accumulation points, interior points, adherent points, and define what a limit is with respect to a function and a point, and when we can say that a function is continuous. Next, we will use these concepts, especially the limit, to compute how the function behaves when we regard to smaller changes in values.